Vroom, vroom, brr, So that was my reenactment of that one scene in the F1 movie that had me sitting in horror, watching an 800-kilogram vehicle be launched 1 trillion meters in the air. Like, surely that's not possible, right? Right? At first I thought the answer was clear, but look here, and here. Some real crashes are so strange, but they're real. So for my HSC physics step study, I'll be looking at the physics of Joshua Pearce's crash in the F1 movie. Let's set the stage. We're at Monza, the Temple of Speed, in the rain, with 2023 F1 regulations. We have Joshua Pearce scrapping with Max Verstappen, post turn 10, approaching the curve of Parabolica. Just before the apex, we see him lose grip, slip, hit the sausage curve, and get thrown at what seems to be an extreme distance. The first thing we need to establish are all the concepts we are dealing with here, and also some of the values that we need. There's projectile motion, horizontal circular motion, centripetal force, and acceleration. The values we need to extract from the footage and various sources are as follows. Just before we start analyzing the scene, I'm going to do a brief overview of key concepts. Projectile motion is a two-dimensional movement of an object, where the only acceleration it experiences is that of gravity in the y-axis. It requires three main kinematic formulas as shown here. Note that as we break down a problem into x and y components, when we work on the x-axis, all values tied to acceleration become zero. Horizontal circular motion in this case is used for cornering and is a direct substitution of centripetal force for frictional force. If we have a circle of radius r and 2 points characterized as the change in velocity where v1 and v2 practically equal each other, if distance between is minuscule, we can use vector addition to form two similar triangles, making substitutions for displacement and then rearranging the formula, we get v squared on r is equal to delta v on delta t, which is the acceleration formula. As force is F equals ma according to Newton's second law of motion, where acceleration is directly proportional to force, centripetal force is therefore equal to mass times centripetal acceleration. Google Earth and Google Maps are going to become very helpful friends with this, as thankfully the track the scene is racing on happens to be real, as in it is the one and only Autodromo Nacional Monza. By setting keyframes of 3 points, we can calculate the distance between these points, where point 1 is an initial point along the straight, point 2 is where the car slides off, and point 3 is the crash zone. Using Street View, we can properly analyze these points to line them up on a Google Earth file, where we see the distance between point 1 and point 2 is 778 meters, and point 2 and 3 to be 71 meters, for a total of 849 meters. We also know Monza is 5,793 meters total, so points 1 and 2 relative to the track are 4,452 meters and 5,230 meters. Analyzing the film, we can get an 18-second sequence between point 1 and 3, and they were even nice enough to give us the average speed in the film of 200 miles per hour, or 89.4 meters per second. So when we plug this in to a basic speed distance formula, we should get a distance of 849 meters. Okay, so obviously they just chucked a random speed into the film, so plan B is to find the data ourselves. We need wet race data, but the last time we had a wet race in Monza was 2017 with a lap time of 96 seconds, and 2018 the next year, where it is dry. We have a lap time of 80 seconds. Adjusted for a 1.02 second increase in speed between generations, we get a speed differential of 83% between wet and dry races. As stated before, the scene concerns 2023 regulation cars, so using Verstappen's time at the real Monza race, we get a time of 71 seconds. Using tracinginsights.com, we can find his instantaneous velocity at 4,452 meters, 5,230 meters, and 5,289 meters. Adjusted, we get 250, 178, and 158 kilometers per hour. I'm not going to bore you with any more details, so let's get into the fun stuff. According to the regulations, these cars were 800 kilograms. Looking at the scene, we get a 4-second flight time for the projectile motion. Now, without initial values and the use of Pythagorean identity to fill in the unknown values, we get the velocity needed to be 95 kilometers per hour at a launch angle of 47.94 degrees and a height of 19.59 meters. I was about done until I found some BTS footage. Knowing everything was done practically reinforces that the crash was indeed realistic, but analyzing the footage, we get a lot of enlightening statistics. Using a frame of the launch and a digital protractor, we get a launch angle of 30 degrees. They also state that the crash was 100 meters away from the launch point, not 71 as I thought. Using another frame of the maximum height of the projectile and using pixel measurements with the fence and barrier for reference, we get a height of 11 meters. Plugging these values into the free motion formulas, we get a coherent and mathematically sound conclusion with 105 km per hour launch velocity and a 10.73 meter height. But would the moments prior to the launch be possible? For the car to slip and cause the crash, it needs to first overcome the centripetal force. Using Google Earth and Illustrator to draw a 1mm to 0.725 meter scale circle, we get a turning radius of 88.4 meters. At the apex, we then get a centripetal force of 7,843 newtons. We can then say the frictional force must be equal or more than the centripetal force to keep the car on track. The friction is found by multiplying the normal force by the kinetic frictional constant, which for F1 wet tires is 1.05. The normal force will be the weight added to the downforce, which in this instance, using a constant and wing area given by Max Taylor, we get a force of 9,400 newtons acting downwards, which gives a friction of 9,870 newtons. Considering it is a turn, we can employ the traction circle to find the feasibility, where we can compare the braking and turning to the max frictional force using Pythagorean theorem. Knowing the frictional force and required turning force, we can deduce a maximum allowable force for braking to be 5,992 newtons. And if we use the acceleration formula, we get a deceleration of 1.85 meters per second squared, which when plugged into the force equation, we only get 1,480 newtons, way lower than 5,992 newtons. So he shouldn't slip then. That is until we see that Joshua isn't on wet tires, and is actually on medium slick tires. In the wet, these only have a frictional coefficient of 0.4, so redoing everything, the frictional force exerted is only 3,760, which is lower than the required turning force, let alone both the braking and centripetal force combined, so I deeply apologize for doubting the authenticity of this scene. As yeah, Joshua would most definitely, in these circumstances, flip off the road at 105 kilometers per hour and get launched at 30 degrees, reach a height of 11 meters, and land 100 meters away from the track, due to not having enough grip to maintain a braking force of 1,480 newtons and a centripetal turning force of 7,843 newtons.